week we are learning a little bit about how materials hold together based on inter and intramolecular forces, and we'll be doing this in a lab where you will be burning different types of compounds and determining which types of compounds burn easier, and to begin to think about why and create scientific arguments about why that is. So here's a little bit of background that might be able to help you with creating those arguments. In a material, we have both inter and intramolecular forces. The word inter means between separate molecules or separate formulas, compound, and intra means within a molecule or within the formula unit. So in a covalent material, for example, the covalent bonds between different atoms are intramolecular forces because they are within the molecule, but any kind of interactions between separate molecules would be an intermolecular force. Some of those could be hydrogen bonds or van der Waals attraction, which happens because of the electrons and protons just being attracted to one another even though they're in separate molecules. So, just to remind us a little bit about covalent bonds and ionic bonds, in a covalent bond, the electrons are being essentially used by both atoms involved to complete their octet. But these might require a certain amount of energy to break, and in fact they do. And here is a list of some of the different energies of the bonds. And the higher the number, this means the harder that bond is to break. And so, depending on what atoms are involved, it could have higher amounts of energy. For example, a bond between a hydrogen and a fluorine has a bond energy of 569, while the bond between hydrogen and carbon only has 415 kilojoules per mole. So that's how much energy it would require to break that bond. The hydrogen and fluorine bond, therefore, must be stronger. Also, we notice that as bonds move from being a single bond up through triple bond, the strength is increasing by large amounts. So when it went from single bond to a double bond, it increased by almost triple the amount of energy. And when we went up to the triple bond, it pretty much doubled once again. So that energy is very high to break this triple bond, meaning that is a very strong bond. Alright, okay, so this is also true when we look at ionic bonds. They have bond dissociation energy. And when we break these bonds, it's going to require a certain amount of energy, and forming bonds also releases some energy. But one interesting thing about ionic compounds is that they interlock in this crystal structure where it's a repeating pattern of positives and negatives. And this is one thing that causes the overall material to be very strong. Now, this packing together like this, since it's technically between separate formula units, like if this was a sodium atom and this was a chlorine ion, these two right here would be considered a formula unit. That's just one sodium chloride compound. But the whole thing being packed together like this, these are attractions between separate formula units, so this could be considered more of an intermolecular force or between separate compound units. Okay, so to also understand a little bit of why we're going to be thinking about the energy involved and the strength of bonds, we need to understand the difference between physical and chemical changes at the molecular level. So a physical change is some sort of change to the physical properties of the substance, and one thing that this could involve that's related to what we're talking about is disturbing the intermolecular forces. So like I just said, that crystal having a whole bunch of NaCl compounds attracted to each other This is intermolecular forces, the two separate compound groups. All these groups being stuck together like this, these are intermolecular forces. So once you put a crystal of salt in water, we all know what's going to happen. It's going to dissolve. And this is because those intermolecular forces can be disturbed. It also is disturbing our intramolecular forces here because the chlorine and the sodium are separated from one another. But as soon as we remove all this water, the chlorine and the sodium can go back to one another and reform that ionic bond, which is really just the positive and negative charges being close to one another because of electrostatic attraction. Okay, so then when we get to chemical change, this is a bigger change happening because at the molecular level, the bonds that are formed between separate atoms are no longer going to be the same bonds. Now, it doesn't mean that every single bond has to change. It could be just one small change. But one example of a pretty big change is any kind of combustion reaction, which combustion is when we are burning something, and we will be burning things this week, so that's why I'm using this as an example. This causes alterations to the intramolecular forces, or the bonds within the compound, ionic or covalent bonds. And what I mean when I say that is all of our carbon-hydrogen bonds in this propane molecule are going to react with oxygen-oxygen bonds. The oxygen-oxygen bond will be broken, and so will the carbon-hydrogen bond. And it's going to basically rearrange our atoms. So now carbon will be attached to oxygen, and oxygen will be attached to hydrogen, and we're also going to have something else released. Heat. Okay, so when energy is released, this means that our reaction is exothermic. And we'll talk about that in just a second. But the big thing here is that chemical change means that our bonds have changed, or intramolecular forces have changed. The easier it is to change those, the more you could assume the bond would be weak. But let's also remember that in ionic compounds, it's not just a matter of how strong or weak the individual bond is, it's also a matter of how strong or weak the whole crystal is, because it has all these forces added together to make the whole structure pretty strong. Whereas the covalent molecules just have their individual intramolecular forces holding them together. And so it doesn't come across as strong in the burning reaction that we're going to observe. Okay. All right, so what is a chemical reaction? A chemical reaction is when we boil it down, just breaking and or forming bonds. So technically we could have, I spelled breaking wrong. Technically we could have a chemical reaction where bonds are just broken, or a chemical reaction where bonds are just formed, but most often it's the combination of some bonds breaking apart and then new ones forming. Now the question is, why does this happen? And the answer to most things in science is it happens because of energy. And that is also the case here. Chemical reactions happen because the molecules or the atoms involved are in some state of energy and are moving to some other state of energy. Now they normally, if they're happening by themselves, it's because they have a higher amount of energy and they're moving towards a lower amount of energy, and that causes it to happen without anybody forcing it to happen. But some reactions can actually be forced to happen by adding energy, and that is also provides enough energy for the reaction to happen, and then it can move to some lower energy state. So the answer to this is to decrease overall energy. that brings us to exothermic and endothermic processes. So let's remember, in a chemical change, breaking bonds requires a certain amount of energy, and forming bonds actually releases energy. So, as you can imagine, some amount of energy has to go into our material for the bonds to be able to be broken, but then once they form new bonds, energy will be released. And so these graphs kind of show that. Our reactants, or the stuff that we had before the reaction, is on the left, and this uphill part of the curve right here is the amount of energy it takes for the bonds to break. Alright, then as you can imagine, as we go back down the hill, that's the amount of energy it takes to get to our product. And this is actually the amount of energy released when bonds form. It's a little bit of a simplified explanation, but it might help us understand pretty well. Okay, so if less energy is required to break the bonds, then the amount of energy that is released, like in this case, we started out at a higher energy level than when we ended up with our products. So that means overall, extra energy was released. And that is something that would feel, let's see, energy is released, and that energy in this graph would be in terms of heat. Energy released as heat. And so if you were holding a flask and a reaction like this happened where more energy was released, then the flask would feel hot. Okay? So this would mean that it is hot, which we call exothermic, when the reaction releases heat. Okay? Now, on the other hand, if our reactants are at a lower energy than our products, meaning that it required more energy, this is the energy required to break the bonds, then energy that was released then in that case the energy would more be absorbed from the surroundings than the amount that's released. And so overall this would feel cold because it's actually taking heat away from the surroundings. So this would be cold, it would feel cold, okay? So we can imagine that if something is releasing heat, it would make sense that because more energy is released when the bonds form than the amount of energy it took to break, we would imagine that that's very likely to happen on its own or because it has enough energy to happen. A lot of times endothermic reactions wouldn't happen necessarily by themselves, but there are some that once you mix certain chemicals, this reaction will happen spontaneously, even though it has to use up a lot of energy to happen. Okay, so we're going to think about that this week in the labs that we're doing and use this information to kind of help us come up with an explanation of why certain materials will burn while other materials will not burn.